Okay, we are officially live. Sorry for the delay. We had some technical difficulties. All right, so my name is Kathy. I'm one of the organizers with SecTalks Sydney, and I will be doing a quick introduction for the first timers, and also I will be passing on to the main speaker afterwards. So, okay, what is SecTalks? We are a nonprofit and independent community that runs monthly technical security talks and hands-on security challenges, like CDFs. We have presence around the globe in Europe, US, Australia, Asia, and everywhere. We try to deliver high-quality content, and we also really welcome anyone who's interested in presenting about security topics and creating CTF challenges for our monthly Ninja Nights. And SecTalks wouldn't be possible without all our lovely sponsors. And if you're interested in sponsoring SecTalks, please reach out to the organizing team. Here are some key links for SecTalks. Most of these can be found from our official website. Please pay attention to the top 2 links. We're actually seeking speakers and call for CTFs for events that's from June onwards. If you're interested, please submit your talk or CTF challenge via the links. If you haven't already, join our Slack channel to stay in touch, and also we will sometimes announce events in the channel as well. And lastly, normally we would have after-session networking at OnTide in Barangaroo. Unfortunately, we are still hosting virtual sessions this year so far. If you would like to stay in touch and network, once again, if you haven't already, join the Slack channel to stay in touch. We will be aiming to host some more in-person events towards later of the year. We're thinking June at this stage. Fingers crossed for that. And that's all from me. I'll be passing to Pedram to introduce.
I think I was talking with myself. All right, let me start again. Okay, good evening, and thanks for joining us, 2021, and this is our first talk in this year. Our speaker has been recommended to us, and we were really lucky to secure a time in his busy schedule to bring him here and do a talk. Just quickly, if you have any questions, like always, you post those questions on the Slack channel. If you are not part of the Slack channel, send us an email, sydney@sectalks.org, and you will receive the email. Otherwise, you can ask your question on this YouTube live chat. All right, with that, let me just quickly move into the speaker by saying, if you are interested in low-level stuff, even something lower than a hardware stack, this is a talk that you're gonna enjoy the most. So our speaker is an author or a developer behind the world's first operating system, kernel, with a formal proof of implementation correctness. And this still is the only capability-based kernel with such a proof. And currently, the functional correctness proof exists for ARM v7, 64-bit systems, and RISC architectures. And in the talk, he will provide an overview of the seL4 microkernel, its verification story, which would be quite exciting and interesting to hear, and some real-world deployment of this kernel. Our speaker is a professor and John Lyons Chair of Operating Systems at University of New South Wales, Sydney, and a Chief Research Scientist at SYD0x40. He's a founder and a past leader of Data61's Trustworthy Systems Group, which pioneered large-scale formal verification of the systems. So, and lastly, he's a fellow of the ACM and IEEE and the Australian Academy of the Technology and Engineering and ACM Distinguished Lecturer. So without further ado, let's welcome Professor Gernot Heiser to talk about SL microkernels, mathematical proof of security.
Thank you very much. Pleasure to be here. I'm not used to give a talk sitting down, so I like to be animated. So, let's see how this goes. Just one comment. If you have questions, I'm happy to be interrupted by questions. So if you guys are monitoring the Slack channels and there's questions coming up, please let me know. So yeah, the seL4 microkernel is something we originated more than 10, 15 years ago on the back of previous 10 years of research in microkernels as a basis for secure systems. And in the 12 years since we originally published about seL4 and its verification, we've been working on pushing the technology further, both on the research side, addressing problems that haven't been addressed so far, as well as investing heavily in technology transfer. So seL4, when we built it, from the beginning was designed for the real world. We wanted a system that people will actually use, not an academic toy. So what is seL4? If you're into operating systems, you probably have heard of it. If you're not particularly into operating systems, you may not have. In a nutshell, it's an open source, high assurance, high performance operating system microkernel, where the microkernel, the operating system kernel, is the part of the software that operates in the most privileged mode of the hardware. So the thing that is most dangerous in a way, in the sense that anything that goes wrong in the kernel, you have no protection against. A microkernel is a particularly condensed version of an operating system kernel that's reduced to the bare minimum. So only the features that need to run in privileged mode are in part of the microkernel. Everything else is exported to user level. High performance, we claim it's the world's fastest microkernel. It's high assurance. This is the proof story I'll talk about. And open source, it's freely available on GitHub on the GPL v2 license. And oops. So the idea is you have hardware. On top of the hardware directly is the seL4 microkernel, which is basically a small layer of software that really just securely multiplexes the hardware and allows you to componentize your software stack that's running on top with bulletproof isolation between the different components. And that means you can securely have coexistence of untrusted and trustworthy software in the same processor. So anything that's not specifically trusted, we always assume as arbitrarily malicious, and we want to guarantee that the system operates correctly in the presence of this malicious hardware. So arbitrarily malicious basically is just another way of saying it's compromisable. We have to assume it does get compromised and therefore behaves maliciously, even though it may not be designed as to be malicious. So because of these properties, seL4 is what I would claim the most trustworthy foundation for building security and safety critical systems. And people have realized this and are using it across a number of domains. So we are seeing partially already actual deployments or projects that are in progress towards deployments in a number of domains, including autonomous driving, a lot of military work. Not surprising, the defense people tend to be the most security paranoid and are most willing to bet on new technologies. Space satellites, critical infrastructure, communication devices, all this SEL4 is making its way into. Okay, so this is the background. Now I made two claims. The performance claim, where I say that this is the most efficient, the highest performance microkernel there is. I cannot give you a complete proof of that, only a partial proof, because both of these systems are closed source. We can't get our hands on, but I do know that other microkernels you have heard of, QNX, for example, Green Hills Integrity, they tend to be about a factor of 10 slower. And I know that not from our own measurements, they didn't allow us to do that, but from custom evaluations of these systems. There is a interesting data point though on performance that is public. And this is researchers, colleagues of mine in China, Shanghai Jiao Tong University. They did a number of papers recently where they try to use advanced hardware support mechanisms to make communication faster. In the process of that, they compared 3 different open source microkernels in terms of performance. That was seL4, the fiasco.oc microkernel, which is a related system from Germany, and Zircon, which is Google's new microkernel, and compare the performance. The numbers you see in this table here are latencies of the basic fundamental message passing mechanism, so to get messages across these hard isolation boundaries. So because their latency is small is good, and you can see that seL4 is about a factor of 3 faster than Fiasco and about an order of magnitude faster than Zircon. Even though when they did the one paper, they picked a version where we had a temporary performance regression about 50%. That's very annoying. I got pretty angry when I saw that. And but we still have factor of 2 headspace compared to the others. So I'm pretty confident with my claim that this is the world's fastest microkernel. The sources for these works are there. You can follow them up yourself. So this is the performance claim. I'm pretty comfortable about this. And the real uniqueness of seL4 is its mathematical verification. And as was said in the introduction, seL4 was the first ever operating system microkernel with a functional correctness proof. So a proof of implementation, fault-free implementation. So what does that mean? Like any high-performance operating system kernel, seL4 is implemented in C. There's a few bits of assembler. We try to keep that to the absolute minimum. It's almost all C. And so we have a C implementation, which we want to say in some sense is correct. In order to do that, we need a model, a formal specification against which we want to verify the C implementation. So this is an abstract model, which is a very precise description of the allowed functionality of the kernel in a mathematical logic. It's an operational description, so it specifies for every function, for every invocation of the kernel, what the effect of that is in this mathematical logic. And then the functional correctness proof says that under the semantics of the C language, the implementation is a refinement of this abstract model, which means nothing else but any behavior that the C implementation can exhibit under the semantics of C is allowed under this abstract model. So in that very strict sense, the implementation is bug-free or functionally correct. So this is what we published first 11.5 years ago. As I said, it was the first ever of this sort. It's a machine check proof, which is really important because the size of the kernel is about 10,000 lines of C. The size of the proof at that time was about 200,000 lines of proof script. So you imagine if this was our pen and paper proofs, it would be completely worthless because there would be more bugs in the proofs than in the actual C code. But these are machine check proofs that are done in a theorem prover tool that basically allows you to only do assert things that it can be proved in the mathematical logics that's incorporated in this theorem prover. And the theorem prover has a small proof checker which runs through these proofs and then says, yes, this proof works out. So in that sense, these 200,000 lines of proof make sense. In meantime, our complete proof base has grown to over 1 million lines. Most of this is actually written by humans, amazingly. Obviously, you have higher productivity than with C because the language is much more strict, much more safe than a C program. That itself is a really great result because it means that we can reason about properties of the kernel at the level of this abstract model, where it's much easier to reason about than C code. But it still means we are at the mercy of the C compiler, and everyone wants to use GCC. And of course, GCC is a big, ugly beast, which is full of bugs itself. So you don't really want to trust this. Also, C doesn't actually have a formal semantics. So we had to formalize C, and parts of C are actually ambiguous. So you basically need to restrict yourself to a subset of C. And we'd have to assume that the compiler has the same assumption of the semantics of the subset, which is not a nice thing to have. So we avoid this by proving translation correctness. So we have this binary, which is produced by compiler and linker, and so that's what actually runs on the processor. And we have a separate proof toolchain that shows that this is a correct translation of our C code. And then we know, okay, the compiler has not managed to insert additional bugs, which is nice. And of course, these proofs compose. So that means now we can reason about properties of the system at the level of the abstract model, and we know it holds for the actual executable binary that's running on the silicon. That's nice. And it's obviously very powerful, but of course, there's no guarantee that the abstract model itself is good. So there's a further work required to show that this abstract model has the right security properties. So specifically, we want to show that the kernel, as described by this abstract model, can enforce the classical CIA properties of confidentiality, integrity, and availability. And we did that too, again, with interactive theorem proving. So this added another few 10 to 100,000 lines of proof to the whole thing. And now we have this complete proof chain from the high level security properties down to the binary, meaning we have proof that the code that runs on the silicon is able to provide you these security properties in an actual system. As I said, most of these proofs were done by interactive theorem proving, which basically means manual work in this theorem prover, but machine checked. The translation correctness was done by a tool chain. I'll explain in a second how that works. So it's a different kind of proof than the others. So this is the function correctness proof was done 11.5 years ago. The other proofs were done over the following 4 or so years. So it's now 7 or so years all up that we did this first thing. It was the first and for a long time the only one. Actually, originally I thought we'd have a window of about 3 years till someone else repeats it. It took about 9 years till there was the first other functionally correctness proof of an operating system, but it's like a toy system. In the meantime, there's another one that is less of a toy that's actually done in industry, specifically for trusted execution environments in ARM Trust Zone, but nothing of this generality as seL4. And in particular, there is no other verified kernel that has a security based access control model, a capability based access control model. I don't want to get into that detail, what capabilities are, etc., but they're basically a mechanism to have really fine-grained access control in a system where you also can formally reason about it. So anyone who builds an operating system for security inevitably uses a capability-based access control. It allows you to, for example, follow the principle of least privilege, which in the alternative models as like access control lists as they are implemented in Linux or Windows, you just can't do. Okay, so the whole proof chain exists for ARMv7. Meanwhile, we have done the functional correctness proof also for 64-bit Intel processors, as well as just about half a year ago completed for 64-bit RISC-V processors. So the new Open RISC-V architecture is now fully supported. The translation correctness, again, we originally did for ARMv7, so that's 32-bit ARM processors. We just completed that for RISC-V. This is sort of an unofficial announcement. We haven't officially announced it yet, but it is complete, and you'll hear about it in the next few weeks. So we now have the complete proof down to binary for RISC-V as well. And we're working on the security proofs for RISC-V. They exist only for ARMv7 at the moment. So this is sort of what the proofs are at the very sort of high level view of them, but what do they really mean? So the functional correctness means that, as I said before, the behavior of the C code is fully captured by the abstract model. And as I said, this means that we can prove further properties at the abstract level. And this is what we did, for example, the security proofs. We showed that the abstract model can enforce those security properties, and therefore, by transitivity, the binary of the kernel can do that. Functional correctness is a very strong properties. It implies a lot of other things no one else has. So specifically, it means that because the abstract model is well defined, kernel behavior is well defined. So you can never have undefined behavior. And of course, undefined behavior is typically what people use for attacks. If you have a stack smashing attack on your kernel, that basically means you get the kernel in a mode where its behavior is undefined because it defines on what data the attacker injects. In seL4, these attacks are categorically ruled out because of the functional correctness. Functional correctness, among others, guarantees that all array accesses are safe. And so you can't have a stack overflow, you can't have any other buffer overflow. There's provably no null pointer dereferences. So any user input is sanitized correctly, provably, etc. So a lot of, basically, just about any of the standard attack vectors on operating systems get ruled out completely. There's some other nice properties, including there's no memory leaks in the kernel. Access control is decidable, which is important for reasoning about security of the system, etc. So this is only a subset of what this functional correctness means, and it's itself is much more powerful. Any sort of assurance, whether it's by formal proof or by traditional testing, is always based on certain assumptions. You can't get around assumptions. So the question is, what are the assumptions? The nice thing about formal verification work is that you need to be explicit about your assumptions, because if you don't state an assumption, the proof will not go through. If the proof depends on something that is undefined, you can't prove it, right? So one of the really nice things of doing this formal verification is it does force you to make all assumptions explicit. And that's already a big difference from what people have normally. And it's really important, because in the end, you can formalize the cyber world, but not the physical world. And at some stage, they need to interface. And this is where your assumptions come in. And a good way to attack systems is often by the assumptions, because people make assumptions that are not really explicit, and they may not be completely fully aware of themselves. So in our case, the assumptions are relatively, there's very few of them. One is obviously the hardware behaves as expected. That's a big assumption, because hardware is buggy, but it's not a thing we can do anything about it, right? It's someone else's problem. and there's people working on that, but it's an assumption we have to make. And I'll get back to that a bit later. So we need a formalization of the hardware-software contract, the instruction set architecture. And the assumption is then, does the hardware behaves according to this? Now, in the past, this formalization of the instruction set architecture had sort of to be retrofitted, and in Intel architecture, that's still the case, but both RISC-V and ARM now have a official blessed formalization of the instruction set architecture. So, and in RISC-V, it is the golden model. So everything goes back to that formalization, and the hardware people test the correctness of their hardware against this formal spec. So that's already a big step forward compared to 10 years ago. But of course, what we really eventually want to see is that the hardware people verify their implementations against that same spec. Until they do that, we have to assume that the hardware doesn't have bugs, doesn't have Trojans, etc. And of course, if you get really security paranoid, think of like critical infrastructure or defense equipment where you're dealing with nation state opponents, then Trojans are a real issue, because can you really trust the hardware you buy? Reality is you're likely to have either the NSA Trojan or the Chinese Trojan or the Russian Trojan in there, so unless you do it yourself. But this is an assumption we have to make. Then we have to, the next assumption, and this is where I said where the physical world hits the cyber world, you have a formal spec and a mathematical logic. And of course, there's no guarantee that this spec matches what you think it does. And this is sort of where you really, in the end, need to test independently whether your assumptions about the spec are correct. You can reduce this risk by proving properties about the spec, which is what we did with our proof the security enforcement of our kernel model. But it's not turtles all the way down. Eventually, you have to sort of assume that what you read here is what you think it means. If you have enough expertise, then that risk can be made fairly small. We need to assume that the proof checker is correct. That again, this is probably the least worrying assumption, because the Isabelle Hall proofer we use has a small proof checking core that's been used for proofs in pure mathematics and in software verification, protocol verification, etc. So it is used in a wider range of areas, and the risk of a bug being in this proof checker is pretty small. Although there is a project in Germany now to do an independent proof checker for Isabelle, so that will take this risk out of the equation as well. But the important thing, with our binary verification, we don't have to trust the C compiler. So that's a big relief, because, as I said, like everyone, we use GCC because it's what we understand. It gives efficient code, etc. Are there any questions up to this point? Okay. So quickly about how the binary verification works. This is actually an automated tool chain. So all the other proofs are manual theorem prover and interactive theorem prover. The binary is automated. And what does it prove? So we have a C source, which the compiler and linker generates a binary from, where we sort of would like to have some correctness guarantee. But it's actually not the thing we want to prove correct, because in functional correctness proof, what we verify is not the actual C source, but a formalized version of it. We have a parser that understands the C semantics and that reads the C code into the theorem prover to produce a formalized C, which is then what we do the functional verification against. So it's this formalized C where we want to prove that the binary code is a correct translation from. So we are after this proof here. And the process we use consists of several steps. First is we have the formal ISA spec. As I said, for ARM and RISC-V, these are now official. That gives us a formalized binary, same as the C code gets formalized, the binary gets also formalized by running it, by using this formalization of the ISA. And then we have two formalized programs and we want to show the equivalence of them. In general, that's known to be Turing complete, of course, but we're not really facing the general problem because we know the compiler did this translation and we know how the compiler operates. So basically we simulate what the compiler does. And we do that by going upwards and downwards. So from the formalized binary, we go upwards with what we call a decompiler. That takes this low-level formalization of the machine instructions and translates it into a functional graph language that's basically designed for describing control flow graphs. And this is done in the theorem prover, so of provably correct translation steps. And with the formalized C, we compile it down into the same graph language, again using rewrite rules in the theorem prover that are provably correct. And then we have a provably correct transformation of these two programs into the same language, same abstraction level. And then we take this and bit by bit throw it at an SMT solver that then says, yes, these two bits of code are equivalent, or if it doesn't, we either have to tweak them or we found a bug. And in the end, if the SMT solver does that for the complete program code, then we know we're good and we have a correctly translated binary. And so running this through the kernel code runs for a number of hours, and we can, in principle, run it whenever we recompile the thing. So that's cool. It does really hinge on this formal ISA spec, which, as I said, ARM and RISC-V now have. Okay, so this is the verification story on seL4, and the question is, okay, how can I use it? As I said, it's open source. You can download it from GitHub/seL4, and you find both seL4 code as well as all the proofs. So the proofs are open source as well. In principle, everyone can check them. In practice, it requires a bit of expertise to do that, but there's fair people around the world that have this expertise. So that's all fine. But keep in mind, this is a microkernel. It's not something like Linux or Windows that's a full-blown operating system. The microkernel itself exports basically no useful services. It just is this thin wraparound hardware that allows you to securely multiplex hardware. So what an actual system would look like is you have the microkernel underneath, and then you have operating system services that are application facing, which the applications invoke, as well as the applications themselves running on top. So in a microkernel, everything that's a standard operating system service like networking, file systems, etc., is a process itself running at user level. And these different processes, whether they're apps or OS services, they communicate by message passing. That's provided by the microkernel. And as I said, these are put in bulletproof sandboxes. So the microkernel guarantees that two boxes can only communicate if there is an explicit communication channel set up between them. And that's how we can enforce security in the system. And device drivers are also user level. They don't belong in the kernel. So bring your own device driver is not necessarily how you want to write a system. Fortunately, there's a growing ecosystem of open source components that are available partially on the seL4 GitHub and other places, but there's also company building operating systems on top. So one of these is Trendos, and I disclosed that I'm chief scientist for the company Hensoldt Cyber in Munich that developed this. So they did a complete OS that has sort of pretty much what you need for typical embedded system applications. So it has secure boot, a crypto components, a file system, TCP/IP stack, and the required drivers, TLS stack. And they will sell you that. You can get an evaluation kit. They have an SDK that allows you to develop relatively easy. But the really cool thing is not only that it gives you more complete functionality, but they also have a verification story that goes beyond seL4. So it runs on the verified seL4, but they also have a verified key store, and they are working close to verifying their secure boot as well. So these are two of the most critical components in terms of security of the whole thing that are verified as well. Secure boot in this case mostly means a secure way to load things that run on top of seL4, because they actually produce their own chip as well. Trendos runs on both ARM processors as well as their own RISC-V processor. And on their RISC-V processor, they burn seL4 into ROM, so you cannot boot anything else. So the secure boot of seL4 is guaranteed by hardware. They also, for their RISC-V processor, they have a supply chain security story. So this is for protecting against nation-state attacks in the manufacturing process of the processor. Okay, this is all nice. Can it actually be used in real world? Yes, there's a few examples of that. One of this is the DARPA HACMS program that was running for about 5 years, finished 4 years ago, I think. So it's been a while now. And in this program, we work together with collaborators in the US on basically showing that you can make real world systems secure from cyber attack through seL4. And we had a total of 4 autonomous vehicles involved here. No, or not. Some are more autonomous than others. So 2 were the research platforms, a off-the-shelf quadcopter frame, but we only kept the airframe. We replaced the processor board, etc., and basically did a clean slate design of the secure system on top and implemented it. And then the GVR bot, that's a US Army robotics reference platform, where we also showed that it can be used for these kind of land vehicles. And so these were the research vehicles which we used for developing the technology. And then there were the actual military vehicles where we transferred the technology to. So one is the air vehicle, the unmanned Little Bird. That's a autonomous helicopter built by Boeing. They converted an existing helicopter airframe for autonomous flight. And if you happen to get to Scottsdale, Arizona, or actually Mesa, Arizona, a bit further south, you can see it flying around the desert. And it actually flies with a helicopter because the FAA requires a safety pilot, but it flies completely autonomously. And these US Army trucks, they are autonomous trucks. They actually drive around Detroit driver-free. And so they were existing systems, so legacy systems, if you like, that our job was, or actually our collaboration partner's job was, to protect them from cyber attack. And you would think these are military vehicles, they should be reasonably safe. Well, not quite so. DARPA had a red team of professional pen testers, and it took about 2 weeks to completely own the Little Bird. And so not particularly secure. And so we did this retrofit, and in the end, we kept the hackers out. And so the professional pen testers could no longer break the system. And I'll tell a little bit of how this worked. So this is a very high level view of the system architecture of the ULB, this autonomous helicopter. It's got 2 computers, the flight computer, which basically talks to motion sensors, controls the motors, and its job is to keep the vehicle stable in the air and flying towards waypoints. And then there's a mission computer that basically has the high level control. It sets the waypoints, it talks to the ground station for updating waypoints, etc. And they share an internal network. And of course, it's the mission computer that's susceptible to cyber attack because the flight computer only has this internal network to the mission computer. So the assumption was the mission computer gets compromised by one of these sensors, either the ground station link or the camera. The camera itself runs millions of lines of code, or the GPS. So that was the threat model. And initially, this mission computer was a Linux-based system. And basically everything was trusted because anything you could attack, you could leverage to attack the rest of the system, which is what the pen testers did. So the interesting thing was the little bird is expert controlled. So us Australians weren't allowed to touch or even look at the software. So all the work had to be done by the Boeing people. They had 2 engineers, and the engineers had no formal methods background and didn't know seL4 when we started. They knew their system in and out. And over the course of 2 or 3 years, they did this incremental cyber retrofit with our advice, of course, and we delivered components, but they actually did the work themselves. So 2 non-formal methods experts over 3 years for protecting an autonomous air vehicle that's development cost probably hundreds of millions. Also, that's a pretty good deal. So the process was an incremental one. And this is typically how we approach these kind of projects. First thing, you take this Linux system and put the complete Linux system into a virtual machine on top of seL4. Now, security-wise, of course, this buys you nothing. You still have the same vulnerable system, except you have now seL4 in between. So all it does is it adds a little bit of overhead. The overhead is extremely low. But this is the starting point for then pulling the critical bits out. And so the next thing was to pull out 2 things. They put the camera software onto its own Linux system in a separate virtual machine and pulled the local network component out of the Linux system and run it natively on seL4. So we now have 2 Linux VMs and a native component. And the one Linux VM, the one running the camera, is completely untrusted. It's isolated from the rest of the system. Of course, the trusted part still depends on Linux and has a lot of components that can be attacked. So that's only an intermediate step. So next step then was to pull more components out. And in the end, everything that was considered critical that had to be trusted was pulled out to run natively on seL4. Some of these were rewritten and some of these were ported. And as I said, the 2 Boeing engineers did that over a period of 2 years or so. And then in the end, we had a mission, a cyber secure computer, which under the threat models, the attacker team could no longer compromise. And it was flying. We saw it on a test flight flying around the desert. It was hilarious, very uplifting to see this legacy system running on seL4, and the pilot said, yes, it behaved completely normally, all good. Cool. Okay, how are we going for time?
Good.
You can keep going. Okay. So one of the things with seL4 is it's extremely low level. And this has part to do with the design goals. We wanted a system that was suitable for real world use, highly efficient, and very general purpose. So the kernel should not restrict what we could do with it, and be able to reason about security and allow to build systems that follow the principle of least privilege, etc. And so we ended up with something that is even more low level than most other microkernels, because you basically have to bring your own memory management for kernel memory, because all that got exported at user level. And the idea for why we did that was to keep the kernel policy free, so it can adapt to any sort of usage policy you want to have depending on your application scenario. The drawback is that it's extremely low level. So this diagram schematically shows you the second most trivial program you can build on seL4. So I would call the most trivial one is one thing, it starts up and it says hello world, and that's it. The second most trivial is you have 2 separate processes and one sends messages to the other, and that's this one. So A and B are the 2 processes. The boxes inside show you some of the kernel data structures that are used to represent these processes. And everything is user level managed, not really by the application, but by some user level code that needs to deal with that. And so just for the second most trivial example, you have 50 kernel objects or more than 50 kernel objects you need to worry about. So that's obviously not the right abstraction level for building systems. This is a graphical view of a non-trivial but still pretty simple system, the CDCC, which I'll mention later. So this is something that does actually something useful, and it's got thousands of kernel objects to worry about. So not the right abstraction level. So this is why we have then a level on top that carries its own verification story. So we call this CAMGIS, our component middleware, and its whole purpose is to lift the abstraction level onto something you can deal with. So it's a component system, so it has a notion of components, which are nicely represented by boxes and represent something that's encapsulated and secure and independent of other things. And then it has interfaces and connectors which you can use to match up interfaces of different components. And there's different kind of connectors. There's RPC connectors for function invocations, semaphores for synchronization, and shared memory for bulk data transfer. And if you look at the top half of this graph, just components A and B, this roughly represents our second most trivial example that which required you to worry about with about over 50 kernel objects. So now we reduce this down to 3 objects, the 2 components and the connector. And that's sort of a more reasonable way to reason about the system. And as a matter of fact, as engineers, this is typically what we do, right? We draw boxes and connections between them. And so it's a natural representation. It's still more low level than something like UML or AADL. And in the HACMS program, we actually used AADL, or the aerospace people used AADL, which is an architecture description language, architecture analysis and description language, and they have tools for showing certain safety properties, etc. And we did a mapping from AADL, automatic mapping, down to this CAMGIS level. But that was unverified, so there's no assurance about that mapping. But for CAMGIS, we have an assurance story. So if we go back to our UAV, other high-level view of this one is a few boxes that correspond to CAMGIS components, device drivers, crypto component, the Linux virtual machine, etc. So it's still oversimplified. I left a lot of things out. But in this case, for example, you want to show that the Linux system cannot do anything, cannot betray any secrets, and cannot mess with the rest of the system. Well, the integrity of cannot mess with the rest of the system is automatically ensured by seL4 because it doesn't have access to any other memory. And the confidentiality condition basically means you want to show that this Linux thing cannot communicate with the outside world except through the crypto component that encrypts any data and sends it out to the base station, and only the base station has the keys to decrypt it. So this is the sort of security reasoning we want to do, and CAMGIS supports this with a number of different aspects. So one is that we generate the glue code that maps these high-level CAMGIS objects onto, and their communication onto actual invocations of the microkernel. So they're basically C stubs. And this is an automatic process. It's sometimes security critical, but in most cases not, because these are only code that executes within a particular connector and so can't leak data outside, for example. But then from this CAMGIS description, CAMGIS has its own description language where you describe these components and connections. We generate the low-level seL4 description automatically, and that generation comes with a proof. So that means we have a proofly correct mapping from this high level down to the low level seL4, where we then can reason about where we know seL4 does the right thing. And we also generate the initialization code that sets the system up. So after boot, it generates all these objects and puts them in the right, puts the capabilities that give access to them in the right places in a way that is properly represented by this CAMCAS description. And that initialization code generation also comes with a proof. So that means then we have a code sequence that provably boots the system into a state that is properly described, correctly described by this high-level simplified CAMCAS model with just a few boxes. And that means we can now reason about security at this CAMCAS level. So that's a very powerful thing. Conditions apply because these proofs are not quite complete yet. We are working in a project on actually completing those. So eventually they will be complete. At the moment, some of these proofs are done at the model level rather than the C level, for example. But this is in progress and will be done eventually. Okay, cool. So we've done a lot, but it's not yet complete. There's still a lot of work to do. Why? It looks like it's a comprehensive story, right? The unsolved problem, or still largely unsolved problem, is time. So far, the whole verification story of seL4 only gives you functional guarantees. It doesn't give you any guarantees having to do with time. And of course, the time has both a security and a safety aspect. The time means that you may have temporal interference that slows down the execution of something critical. And if that's a critical real-time system, it may force the real-time component to miss its deadline. So that would be a integrity violation. And we have addressed that by extending the model, and that's undergoing verification at the moment. It's probably less interesting for security people. But the security aspect of time is that if there's two components executing, one holding a secret, that's a high component, the low component being untrusted, the low component may, by observing its own execution speed, learn about the secret. And this is sort of the typical timing channel attacks, which got suddenly very well known with the Spectre and Meltdown attack 3 years ago. I was evangelizing about this risk for years, and no one took it seriously until the Spectre Meltdown people, including one of my collaborators from Adelaide, demonstrated, yes, this is an actual real problem, and it's time to wake up to that it is a problem. We need solutions. And with what we call time protection, we work on a solution on this one. So I'll quickly go through what time protection is and how we are using it to prevent timing channels. So there's different kinds of timing channels. Some are algorithmic, where you just have inherently your execution time depends on the nature of a sequence. These are just stupid code, right? And it's not the operating system's job to protect against that. The really dangerous ones are the micro-architectural timing channels, where there's nothing wrong with your program, and yet it leaks data. And these kind of leakage always go back to shared hardware. And they're micro-architectural because this is hardware that's not explicit in the hardware-software contract. The ISA doesn't talk about these things. And that makes them dangerous. So they're hidden by the abstraction. And the ISA is a very useful abstraction. People have been using it for decades as a way to have a clear contract between the hardware manufacturers and the software developers. But it abstracts away anything to do with time. And that means that it's a leaky abstraction when you worry about secrets that have effect on the timeliness of things in the system. So we have the high and the low component competing for the same underlying hardware, and this means they interfere in their execution speed. And this is a difficult problem because everything is hidden by the hardware-software contract. So our solution is what we, as I said, what we call time protection, which is a systematic elimination of these timing channels by strictly controlling any sharing in the system. Obviously, this does not work without assumptions on the hardware, and this is where the limitations come in, and where we're working actually with the hardware side as well, and making sure that we have conformant hardware on which we can actually do this correctly. But the basic idea is, because timing channels result from competing access for the same hardware, we need to prevent this competing access. So we need to partition all hardware. And some hardware can be spatially partitioned. So if we have a normal processor, it has a cache hierarchy, L1 cache, L2, L3, and then memory, etc. Except for the L1 caches that live on core, this can be spatially partitioned. The typical way to do that is what's called memory page coloring, which you make use of the associative lookup of those caches to distribute physical memory, so the physical memory bits given to different components their access to them cannot interfere in the cache. And that's a well-known technique, it's been around for decades. The problem is this works fine for things that are off-core, but not resources that are inside the processor core. So this includes in particular the L1 caches, the translation leukocyte buffers, so that's the MMU, things like branch predictors and prefetchers, etc. They cannot be spatially partitioned because there's no hardware support to do that, and adding the hardware support would be too expensive. It would require replicating all these resources, but also because access to them is by virtual addresses, and virtual addresses are not under operating system control. The application determines which addresses it uses, the operating system cannot. So we can't spatially partition those resources, so we have to temporally partition them, which basically means secure multiplexing. And that means, okay, you let some process use this hardware for a while, and then you hand it over, and in between you reset it to a known state, so it doesn't keep any history dependent state, and then your temporal partitioning is complete. And this works fine. You can't use that for everything, because if you have a shared cache, and typically the last level cache in a multi-core process is shared between cores, flushing doesn't help you. You need spatial partitioning there. So basically, both spatial and temporal partitioning are needed for this. And there's a paper that explains all that in gory detail, which has won the Best Paper Award. So some people think this is useful. And what is required for the temporal partition? Spatial partitioning is just a matter of memory management, although it's not so tricky, because you also have the operating system kernel itself that needs to be partitioned, etc. We've done all that, but that's more sort of grunt work. The question is, okay, what happens with the spatial partitioning? We need to make sure that when we hand over the hardware, so when we do a context switch from one process or one security domain to another one, we need to reset all this hardware to a defined state. So on a very abstract level, this means we do a switch of the user context, which is what the operating system normally does when handing over from one process to another. And then we set the timer to make sure that we get interrupted again when the time slices up. And in between, we need to make sure that we remove any history dependence from the hardware. And we do this by flushing all this on-core state. So that's in principle easy and fine. Turns out if you have an Intel processor, which of course all these things have, anything that's not a mobile device, an embedded device or mobile phone or something like that, you don't actually have the right instructions for doing that. Intel could really fix that very easily in their microcode. They don't think it's necessary apparently. But at least on ARM and sensible processors, you can do that easily. But the problem is the latency of the switch itself depends on execution history, because you have a data cache which contains data. Some of it is dirty and needs to be written back when you flush it. And of course, the time you need for flushing it back depends how much dirty data you have in the cache. Okay, so we need to pad this. So we take a timestamp and then we do the flush and then we execute a loop until we reach the worst case flush time, and then we theoretically save. There's a little bit of shared data, kernel data left, which we need to also specifically deal with, and then we should have a completely deterministic partition switch, and the new partition starts with all the shared hardware in a defined state, and there should be no timing channels. That's the theory. And we went and tested this. So we did what's called a prime and probe attack, where we have a Trojan on the high side, which actually actively tries to leak the secret to an attacker on the low side. So this is if you have compromised code, right? Your code that holds the secret is compromised, so it's malicious. Or in the SecTalks attack, they actually constructed a Trojan from gadgets. So people often say SecTalks uses a side channel. It's actually not true. A side channel is something that operates without actively leaking. It's incidental leakage, but they constructed a Trojan that actually actively leaks the data. So it's a proper covert channel. And people in the past who often said, yeah, covert channels are not interesting. The military may worry about them. I worry about side channels only. SecTalks showed that side channels is not the only problem. Covert channels are. So we take this worst case approach of having an actual covert channel where the Trojan tries to leak. It encodes information in a cache footprint. So it touches fewer or lesser parts of the cache. The attacker first primes the cache, so it fills it with its data. Then it lets the Trojan execute, which touches a subset of the cache lines, encoding the secret in that subset. And then the spy runs again and observes its execution time. So the input signal is the secret encoded by the Trojan. The output signal is the measured execution time, which the spy observes. And if we do that without any countermeasures, we get a beautiful channel. So what you see here is the so-called channel matrix. It shows the leakage as a conditional probability of observing a specific output value given a specific input. So it's a heat map. Yellow means high probability, black means 0 probability, and conditional probability of observing a certain output value, let's say this 5,000 here, as a function of the input value. And you can see the probability is very hot around 32. So if the attacker observes an execution time of 5,500 cycles, it can with very high probability conclude that the input value was 32 plus minus 2. So that's a very strong channel. But in channel, you have a channel whenever in the channel matrix you see a variation of probability along a horizontal line, as this is shown here. Okay, so we apply our time protection, and for this decache, works beautifully. All we see left is random noise. There's no channel left. There's no structure along horizontal lines. Cool. Okay, let's look at some of the other channels. There's the branch predictor, which has a component called the branch history buffer, which the way we evaluated it is just a 1-bit channel. So there's only 0 and 1 values. You see a very strong structure in this channel matrix, so very strong channel. We tried to wipe it, and it's a bit hard to see, but if you go to the right figure here, you can see there is a bit of a discontinuity here. So there is still a channel. And this is by throwing everything the hardware gives you at trying to get rid of this state. So basically, this processor has inherent channels you can't get rid of. It got microarchitectural state you cannot clean. So that processor is inherently insecure, at least as terms as timing channels are concerned. Turns out this is not restricted to the Skylake processor nor through Intel hardware. We did the same with ARM. This is again the branch history buffer on an ARM Cortex A53 processor. Same thing, the channel is much stronger. You can see on the right side, there's a very clear channel here. And we did a study of taking a number of different Intel and ARM processors and try to eliminate those channels, and we found remaining channels in all of them. So basically the takeaway is at the moment, there's no hardware that is secure against timing channels. So that's not nice. Fortunately, there's ways out, and we now have an open architecture, RISC-V, and there's open source implementations of it, which you can experiment with. And we did that. There's in particular one open source implementation of RISC-V is the Ariane processor from ETH Zurich, and we partnered with ETH to make their Ariane secure from these timing channel attacks. So the student implemented a flush instruction, which basically gets rid of all this on-course state. And we could show that, yes, this gets rid of all those channels. And we looked at all the channels that are known, or all the attacks against all the hardware components in the processor, and we could not find any remnant channel. So it actually works. One is also best paper. So there's hope. And of course, RISC-V architecture is still a work in progress. It's been actively specified. And I got a lot of traction from the security committee of RISC-V, and we're working on actually getting this right mechanism specified as part of the RISC-V ISA. So future RISC-V processors will be secure. And I mentioned the MIG-5 processor from Hensoldt Cyber. That's an Ariane implementation. Their next version, which is going to tape out in the next few months, has this mechanism in there. So by end of this year, early next, we will actually have actual hardware that has the right properties to get rid of timing channels. So this is still a problem that's not complete. There's still lots of work to be done. At the moment, we have a prototype, and we show that with the right hardware support, the prototype works. So the next thing, of course, is we know real world hardware isn't the right hardware. So we're working on fixing the hardware using RISC-V to drive this. When we can show that this RISC-V processors have the right security process properties, then I think Intel will finally wake up and follow, and ARM as well. So this is work on fixing the hardware, and there's good industry support as well as the RISC-V Foundation support for doing this. The other dimension is making the thing usable. As I said, it's a prototype. It's not yet an operating system that you can actually use. So we're developing this in a usable system model and combine it with our temple integrity model to make a complete story. And then actively working on proving that under the assumption that the hardware has the right properties, which of course we're working on making sure it happens, we can prove that our mechanisms will actually eliminate those timing channels. And this is making really good progress. I think we're through the really hard part in those proofs. It's done at the moment at an oversimplified hardware model, but we've got another year or two to refine that down to the ISA level, and then have a system where we can show that with the right hardware, it can actually completely eliminate microarchitectural timing channels, which I think is nice. And that's the end of my talk. I'm happy to take any questions.
Well, thank you very much. I think very complex problems, and at the same time, amazing work, right? US. So that is over 11 years, if I'm correct.
So we started in 2004 with the first pilot project, and then the actual SEL4 project started in 2005. And so it took us 4.5 years to get the first functional correctness curve. And since then, we've built on that. Yeah.
Beautiful. We have a question from one of the audience here. It talks about, are there any consideration for this to be applied on security hardware products? Things like firewall. I don't know, you don't see the question there. Are there any consideration for this to be applied on security hardware products like firewall? I think you covered it.
Yeah, we're working on secure RISC-V processors. Yeah. And other people working on verifying hardware actually. So yes, of course, hardware is sort of a deep stack, right? You have your system C or Verilog design, and then gets compiled down with a tool chain to a netlist, and the tool chain could contain bugs or Trojans, and then the netlist is sent out to a manufacturer, and they do whatever they do with it, and then it comes back. And there's like several abstraction levels in the hardware itself, and getting all that right will be a long and arduous project. Would be nice to have at least proofs that the VHDLs, the System C implementation, matches the ISA. I think this is where we will see significant progress in the next couple of years. And then getting down to the netlist, that's going to be a lot more work. I had a project with Intel where we were looking at driver verification and try to sort of verify against the netlist. It could be done, but the project in the end didn't get as far as I hoped, because we couldn't really get, even the people in Intel labs couldn't really get their hand on sort of the right artifacts for the devices. So I think this needs to be coming from inside manufacturers.
If you have any questions. I mean, we talk quite a lot.
Let me just set my mic.
Yeah, we talk quite a lot about formal proof. Do you have any example of that you can show? I know there are things in your GitHub repo. A most simplified one.
Not really where I can put my hands on. I have examples of formal spec. Let me just check whether I can find this.
Just another quick example. Like the any details of what process we're using to secure or just to simplify how long to secure my use something easy to apply, or it's needed a lot of engineering to.
So generally, adapting legacy systems requires a fair bit of engineering, because you typically, it depends how well structured your system is, right? If it's well modularized, then it would be it wouldn't be too hard. But as we shown in the Hackham's program, right? This was a thing that all up had, I think the actual representation is of the order of 50 components or something like that. That's okay complexity. It's not a super complex system, obviously, still relatively simple. But so it was doable there, but it took 2 years or so. So it's not trivial. And but in a well-structured system, you have only relatively small components are really security critical, and these are the ones that you need to pull out. And sometimes that can be done in a few months' work. So.
And realistically, like, how far do you think, like, of time it will take for this to be, like, in a heavy commercial use? Like, unless maybe someone like Amazon or Microsoft adapt the usage of.
Yeah. So, I mean, inherently, it's going to be used primarily for quite a while, primarily in the embedded cyber-physical world, where you have relatively simple, from the system architecture point of view, relatively simple systems. And they tend to be fairly static in their architecture, and that eliminates a lot of complexity. A true general purpose system, to build that really secure is actually, it's another project that I have with actually designing, giving you a, let's say, a design pattern for a general purpose, fully dynamic system that could be like a cloud server or a desktop system, etc. And we hope to have a prototype of that within a year, and then sort of starting to reason about that it has the right properties, and then of course turning that into an actual system, meaning filling in all these components, etc. That's still a lot of work, and in particular, it's not yet clear how much effort it takes, for example, to take a Linux file system and adapt it to this general purpose secure system. That's part of a project that I just applied for funding for, so that work still needs to be done. I have an example here. So this is the abstract specification of how the scheduler looked in a early version of seL4. And this is an intermediate level spec. So the abstract level basically says, if you want to schedule a thread, look for a runnable thread and take it. So it has no specification of the actual scheduling policy, for example, no notion of priorities or anything of that. And then the second box is a more expanded version of an intermediate level spec that corresponds to a Haskell implementation of the functionality. And it's only a small section, but this shows, like, talks about priorities and time slices, etc. So this is a fairly detailed specification of how the scheduler operates. And then that maps down into actual C code, but I don't have examples of proof scripts.
No problem. Okay, so I'm mostly asking to see more examples just to get my head around. You mentioned about formalized C code, and I'm really interested to see what is the difference between that and that C code that we just saw. It was in your slide 8, and you mentioned about your formalized C value.
Yeah, I don't have an example of that here, sorry.
I'm not a formal methods guy, so I'm the operating system guy, right? So and I'm not really the right person to talk about the details of the formal verification. And but you're right, I should actually have some examples of this around. That would be a reasonable thing to do.
Okay, no problem. The next question was more, what sort of checks, or I mean, what is the implementation looks like when you are doing a check for stack smashing or like null pointer dereference? Do you have like an example code or something that you in concrete?
Most of that is, it's just C that's written with the assumption that it's safe, and then there's a separate proof to show that it's actually safe. So rather than having runtime checks, it's actually, there's proof that the index space is constrained enough that it cannot overflow.
So, okay, so we don't really have that.
So in some cases, there would be runtime checks. Runtime checks are generally needed when you have data that comes from a user. For example, if you the user stack pointer can't be trusted and things like that. But anything that's inside the kernel, it's restricted. Basically, it uses a strong type system that ensures that there's no out of bounds accesses, and then that gets then translated into type safe C, basically.
Trying to introduce additional types within that, like for example, for that array example. So do we have a specific thing you have defined to enforce those boundaries?
Yes. Yeah. So some use abstractions that are inherently safe, and where they are not, then there's explicit proofs that show that however you get to that point in the code, your pointer is valid or your index is valid.
So most of these,
most of the verification is proving invariance. For example, if you have an array access in a loop, then there would be a proof at the beginning that the index is in a certain range, and then there is another proof that the invariant gets maintained during the loop execution, and therefore you can never have an out of bounds access.
All right. So most of the things, most of the guarantees that you mentioned are proven through the proof, not so much, let's say, unit test, the test that you actually.
We have a test suite, but the test suite is not particularly extensive. It doesn't test a lot of the kernel functionality because we prove it correct. But there's some limitations. For example, we still haven't proved the initialization code. And so, that's not nice, because if there's a bug in the initialization code, the kernel could boot up in an unsafe state, and the proofs assume that the kernel starts in a safe state and then proves that the kernel retains safety. But until the initialization code is completely verified, there's no guarantee that the kernel actually does boot into a safe state. And in the past, we had bugs in there where the kernel turned out to be unsafe and user level could crash it at its control, which is of course not what we want. Initialization verification is technically boring, is not particularly interesting, so that's why it's a background activity. We tend to put new students on it. But so if someone really wants it, if they put money on the table, we'll do it basically. But until that, we have more interesting things to do. And then this is where a certain degree of testing cannot eliminate the need for the verification, but it can be, you can test the system to get reasonable assurance that in all likeliness the kernel did boot up in a safe state. But of course, it's not a guarantee. But it's, yeah, with enough testing, it's, I shouldn't be saying that because we believe everything should be proof correct, but it's, yeah.
So mostly I kind of, that would be another assumption.
Another assumption, yes.
Yeah.
At the moment, that's an assumption that the init code is correct, yes.
Mm-hmm. And there was one, again, it's during slide 8, talking about graph language. Is it like the AST, like an abstract syntax tree, or are you talking about something else that then you compare?
No, it's not a AST, it's a representation of the control flow graph.
Mm-hmm. Yeah, I'm just very interested in more concrete examples, like especially in example you show that it was one of those devices you worked on. It was a slide 10 or something. Maybe if you have the slide, we can talk through that. But you had TCP/IP and a few other components that sit above the your microkernel.
Yeah.
And what sort of guarantee that? I'm just wondering, it provides, like, in terms of like someone write a malicious packet or someone overflow the stack on the TCP, that implementation of the TCP/IP there. Like, is this a concern of microkernel, or this is like out of scope?
Well, so the kernel itself is proved to not having any of these problems. Any actual system you build will obviously have trusted components beyond the kernel. And ideally, you want to verify those. Now, once you have the advantage is, of course, once you have verified your trusted components, or if you can assume your trusted components cannot misbehave, you at least have a guarantee that the untrusted components don't mess with it. In particular, that means the TCP components, trusted computing base, each component can be verified in isolation, because we know the kernel enforces its interfaces, and you can, for each component separately, prove that it conforms to its functional spec, and then the kernel gives you the rest. And depending on how paranoid you are, you want to verify these components completely, or maybe it's enough to run static analysis over them, which doesn't give you the complete proof, but it gives you a high degree of assurance, etc. So you can play a assurance versus security trade-off. You can also play a performance versus verification effort trade-off, because the smaller, the simpler the component is, the easier it is to verify. We've shown in the past that the verification effort scales with a square of the size of or some complexity measure of a component. So by breaking things into fewer components, into more components, you can reduce the verification effort for each in a way that reduces the overall verification effort. But more components, of course, mean more security domain switches, and therefore overheads, because each time the kernel gets involved.
Okay, this is, I mean, I'm trying to understand. So some of my questions, feel free, completely destroy me if it is incorrect. So are we talking about the subset of attacks that we are saying in our microkernel, we have a proof for it, like in terms of like memory safety, one of them, null pointer dereference, and things that happen mostly, let's say, at a network layer, like network types attack. These are not, we can't really provide any guarantee for those, because this is not.
So you can, if you have trustworthy crypto, then your network subsystem, like the protocol stacks and the device drivers, etc., they can only do a denial of service attack. They can't break integrity and confidentiality anymore. So in that sense, you can reduce the security problem a lot by just having a verified crypto component, which is basically the approach Hensoldt Cyber use in their Trendos OS. They say, okay, we don't need to verify the drivers. If we are not worried about denial of service attacks, of course, you should be worried about denial of service attacks, but liveness properties you can actually often prove with automatic tools like static analysis. That's good at proving this kind of liveness properties, which then protect you against denial of service attacks.
Okay, so there are, a category of the attacks we're talking here is we can't really say like our microserver also covers the bad things.
I mean, an operating system can never prevent you from building an insecure system. The system you build on top needs to be structured in the right way, so you can actually reason about its security properties. Of course, the first step is you should actually establish what are the security properties. This is where it typically ends, that most systems don't even have a clear statement of what it means to be secure. So you need to have a very clear specification of what it means for the system to be secure, and then you need to somehow reason that the actual implementation satisfies that. And with the componentized architecture, where the isolation of components is guaranteed by the microkernel, you can reduce that problem to reasoning about the correctness of the trusted computing base, which you can keep small by design, basically.
No, cool. I don't want to make this session to go longer than this, but my kind of final talk is, whoever is interested to start this journey or getting to more security of the microkernels, what would you suggest? Where is a good start? Obviously, come to your lectures.
That would be a good start. Although my advanced operating systems course, where students build an operating system on seL4, is probably much more detailed than you actually need to for building things with seL4. So in practice, I think a better starting point is the seL4 tutorials, and we are also in the process of building what we call the seL4 core platform, which is basically an open source mini OS that's easily extensible. It gives you the right framework for not only building things easier with seL4, but also making sort of by construction, ensuring that you use the seL4 mechanisms the right way, because seL4 to use correctly is not easy. We're working on making that easier. That project for the seL4 core platform is actually funded by a Defense Next Generation Technology Fund project, the plan is to have an actual device that protects a critical infrastructure and have that demonstrated somewhere in the Simpson Desert before the end of the year. So looking forward to that.
Sounds great. Any kind of thoughts or comments or things to make?
No, I don't really know the background of the people here and sort of what your interests are, but if you're anyway interested in further discussion, collaborations, etc., I'm very happy to talk.
I think, and I know you are looking for PhD students to join you.
Always, yes. I'm always after good students.
Well, thank you very much.
Thanks, it was really, really great to have you here. And thanks everyone for joining us. And as you see, this is a defensive talk, as some of you already requested, so we brought it. And if you're looking for speakers and content from at least June onwards, so if there is anything you can help us with, please go to their call for paper. Thank you very much. See you next time.